The question of whether large language models truly learn or simply memorize has become one of the most contentious debates in the tech space over recent years. As AI systems become more powerful and ubiquitous, concerns about what they retain from their training data have intensified. Can these models expose sensitive information? Do they genuinely understand, or are they just sophisticated copy machines? The implications span a number of domains such as privacy, copyright, security, and our fundamental understanding of what these systems actually do. But beneath all the debate and concern, fundamental questions remain unanswered. How much information can these models actually store? When models are trained on trillions of tokens, but only have billions of parameters, what are the limits of their memory? What's the difference between memorization and genuine learning? And can we even measure them separately? And critically, given how much data modern models are trained on, are they actually vulnerable to privacy attacks, or has the scale of training made individual data points essentially unrecoverable? In this video, we will go through the groundbreaking research from a collaboration of researchers at Meta, Google, NVIDIA, and Cornell University, which provides the first rigorous framework for measuring and understanding memorization in large language models. We'll tackle this in the following way. First, we'll explore the traditional methods researchers have used to detect memorization and why they fall short. Then, we'll dive into the new framework that finally separates memorization from genuine learning. Next, we'll look at the actual experiments and results, answering questions such as how much can these models memorize, what types of data get stored, and how this changes as models scale. Finally, we'll answer the critical privacy question. Are your conversations and data actually at risk? Let's get started. For years, the field has relied on two primary methods to detect memorization in language models. The first approach is known as extraction attacks. If a model has memorized specific training examples, then under the right prompt, it should reproduce that information verbatim. Researchers test this by providing only a small fragment of text, often the beginning of a sentence, and observing whether the model continues with the original passage word for word. In cases where memorization has occurred, the model can generate the remaining text exactly, despite being given only a short prompt. The second approach, called membership inference, takes a different angle. Instead of trying to make the model generate memorized text, researchers ask whether the model's behavior reveals if a specific piece of text was part of its training data. To test this, they feed the model a complete sentence and measure how surprised it is, quantified by the prediction loss across the sequence. If the model assigns unusually high confidence and low loss to the text compared to typical unseen examples, the text is inferred to be a likely training member. If the loss is higher, the text is treated as more likely unseen. Despite their usefulness, both of these approaches run into the same fundamental limitation. Neither extraction attacks nor membership inference can reliably distinguish memorization from generalization. A simple example makes this clear. If you ask a model, what is 2 plus 2, and it replies 4, that does not imply the model memorized that exact equation from its training data. It may simply have learned the rules of arithmetic and applied them correctly. The same ambiguity appears in more realistic cases. If a model assigns very low loss to the sentence, "My email is john.smith@company.com," is that because it memorized this specific email address, or because it learned the general structure of email addresses after seeing many similar examples? This distinction is crucial. If a model has memorized a specific private email address, that represents a genuine privacy and security risk. If instead it has only learned broad statistical patterns about how emails are formatted, then assigning low loss to a particular example does not indicate any data leakage. Unfortunately, extraction attacks and membership inference provide no way to tell these two situations apart. Both methods can flag suspicious behavior, but neither can explain its source. So what would a proper definition of memorization actually look like? What properties must it have to be truly useful? First, and most critically, it must separate memorization from generalization. We've already seen why this matters. Knowing that a model outputs 2 plus 2 equals 4 tells us nothing about whether it memorized that specific equation or learned arithmetic more broadly. A good definition needs to distinguish between information the model has about specific training examples versus information it has about the underlying patterns in the data. Second, it needs to work at the sample level. We don't just want to know that the model memorized some of its training data. We want to measure exactly how much information the model retains about each individual data point. This is crucial for understanding privacy risks. It's not enough to know that membership inference works 70% of the time on average. we need to know which specific examples are vulnerable. Third, the definition must be independent of the training algorithm. In practice, we often only have access to a final trained model and a piece of text we want to test. We don't know exactly how the model was trained, what optimizer was used, or what the learning rate schedule looked like. Our definition of memorization needs to work with just the model and the data, nothing else. These three requirements might seem obvious, but they're actually quite demanding. Most existing definitions fail at least one of them. So how do we build a definition that satisfies all three? The answer comes from information theory, specifically from thinking about memorization in terms of compression. The central idea is that true memorization should enable additional compression. If a model has memorized information about a specific data point, then that data point should be describable using fewer bits when the model is available to help reconstruct it. Intuitively, if a short prompt allows the model to recover a large amount of highly specific information, that is evidence of memorization rather than general pattern learning. Crucially, this framework relies on comparison. Researchers evaluate two models, a target model trained on the dataset of interest, and a reference model trained only on general data. The reference model captures what any competent language model would predict based on broad regularities alone. Any extra compression achieved by the target model, any additional confidence beyond what the reference provides, reflects memorization of specific training examples. This comparison makes it possible to disentangle memorization from generalization and to measure unintended memorization directly. To make this concrete, let's start with the simpler case and build up. Imagine we have a training process where we feed in a data set and get out a trained model. Information theory gives us tools to measure how much information flows from the data into the model. In the statistical framework, we can define total memorization as the mutual information between the dataset and the trained model. Essentially, this measures the reduction in uncertainty about the dataset after observing the model. If knowing the model tells you a lot about what data it was trained on, that's memorization. But remember, we need to separate unintended memorization from generalization. Here's where the framework gets clever. We introduce the concept of a ground truth model, a hypothetical perfect model that captures the true underlying patterns in the data. Unintended memorization is then defined as the information the trained model contains about the dataset beyond what's already captured by these true patterns. In other words, it's the sample-specific information, not the pattern-level information. Mathematically, we can decompose the mutual information between the model and the full dataset. The part that represents mutual information between the model and the dataset, conditioned on the true patterns, gives us unintended memorization. The remainder is generalization, information about the underlying distribution itself. This statistical definition is elegant, but it has a critical limitation. It only works for random variables, not individual instances. We observe a single trained model, a single dataset, and a single piece of text we want to test. We can't compute entropy or mutual information from a single sample. Those concepts require probability distributions. This is where Kolmogorov complexity comes in. Instead of thinking about information in terms of probability distributions, this approach measures information in terms of description length. The core idea is that the information content of a string is the length of the shortest computer program that can produce it. Consider the following two strings. Both are 20 bits long, but the first has much lower complexity because you could describe it with a simple program that just repeats a pattern 10 times. The second string has no obvious pattern, so the shortest program would essentially need to store the entire sequence. The key advantage is that this works for individual strings, not just probability distributions. This lets us measure the information content of a single data point. And just like before, we can define a conditional version as the length of the shortest description when you have auxiliary information available to help. If a model has memorized a data point, the description should be short because the model can fill in the details. If it hasn't, you need a much longer description. By comparing how well the trained model compresses a data point versus how well a reference model does, we get a direct measurement of unintended memorization. There is one critical detail, however: this complexity measure is uncomputable, meaning no algorithm can calculate it exactly. However, we actually don't need exact values. It turns out we already have an excellent approximation, which is the model's own likelihood. This gives us everything we need: a way to measure memorization on individual examples, separate it from generalization, and only require access to the final model. But there's still the question of how much these models can actually memorize. What's the upper limit? That's where model capacity comes in. Model capacity is the maximum amount of information a model can memorize across all possible datasets. To measure it, you train models on datasets of increasing size and find the point where memorization stops increasing. Once capacity is filled, adding more data doesn't increase total memorization. It just spreads that fixed capacity across more examples. So now that we have talked about how things work, let us answer some of the questions we asked earlier in the video. First, what is the actual memorization capacity of these models? To find out, researchers train models of different sizes on completely random data, which are uniform bit strings that contain no patterns to learn. This removes generalization entirely, so anything the model keeps has to be pure memorization. When you train models of different sizes and measure how much they memorize, you get a clean linear relationship. The slope of that line gives us the answer, about 3.6 bits per parameter. To understand what that means, a bit is the basic unit of information. 8 bits make a byte, which is enough to store a single character of text. So 3.6 bits per parameter means each parameter can store about half a character worth of information. Now let us scale this up to a real model. GPT-3 has 175 billion parameters. At 3.6 bits per parameter, the maximum memorization capacity is about 79 gigabytes. That is roughly 15,000 typical books worth of text. But GPT-3 was trained on 300 billion tokens, about 2 terabytes of data. The memorization capacity is only 4% of the training data. The model physically cannot memorize everything it sees. For every 100 pages it reads during training, it can only memorize about 4 pages worth of specific information. Everything else has to be compressed into patterns and generalizations. So what does this mean? On one hand, it is somewhat reassuring for privacy concerns. The vast majority of the training data cannot possibly be memorized word for word. But on the other hand, 4% of 2 terabytes is still a massive amount of information. The critical question becomes which 4% gets memorized. Is it random, or do certain types of data get stored more than others? And if your private email or personal information happens to fall into that 4%, the capacity limit offers no protection at all. So let us answer that question. What determines which 4% gets memorized? When you plot memorization against TF-IDF scores, which measure how rare the words in a sequence are, there's a clear positive correlation. Sequences with common, frequent words show near zero memorization. The reference model predicts them just as well, meaning they're learned patterns, not memorized specifics. But sequences with rare, unusual words show high memorization. Looking at the actual most memorized sequences from a 20 million parameter model makes this concrete. They're sequences in Japanese, Chinese, Hebrew, and Greek, languages that were underrepresented in the training data. These rare sequences get stored verbatim because the model can't extract generalizable patterns from just a few examples. This has direct implications for privacy. Your mundane everyday conversations are likely learned as patterns, not memorized word for word. It's the unusual, rare data that's at risk. If your email happens to contain highly unusual phrases or rare language combinations, it's more likely to be stored exactly as it appeared. But generic common text gets compressed into statistical patterns. Now that we know what gets memorized, let's look at how this changes as datasets grow. When you train on real text instead of random data, something fascinating happens. Unintended memorization rises at first as models fill their capacity with sample-specific information, but then it peaks and begins to fall. For the 19.2 million parameter model shown here, unintended memorization peaks around 10,000 to 100,000 samples, then decreases as the dataset grows larger. The model is trading unintended memorization for generalization. When the dataset is small and fits within capacity, memorizing individual samples is efficient, but as the dataset exceeds capacity, the model shifts strategy. It starts storing reusable patterns instead of specific examples. The total information in the model stays constant at that 3.6 bits per parameter limit, but the composition changes from specific sample information to generalizable pattern information. We can verify this by looking at extraction rates, which represents how often you can prompt the model with a prefix and get the exact training continuation. For small datasets, extraction rates are nearly 100%. But as dataset size increases to 1 million or 10 million samples, the extraction rate on training data converges exactly to the extraction rate on test data. Successful extraction isn't actually memorization anymore. The model is generating plausible text based on learned patterns, not regurgitating memorized sequences. This confirms that models don't just memorize or learn, they do both simultaneously, and the balance shifts predictably based on the ratio of dataset size to model capacity. Finally, we take a look at the question everyone wants answered. Are ChatGPT, Claude, and other modern models leaking your private data? Researchers developed a scaling law that predicts membership inference performance as a function of the capacity to dataset ratio. Membership inference is the ability to detect if specific text was in the training data. For small datasets relative to capacity, it works extremely well. But as the dataset grows larger than capacity, performance degrades dramatically. When your dataset is much larger than model capacity, membership inference approaches random guessing. The scaling law was validated on large models. The researchers predicted exactly what dataset size would produce specific membership inference scores on GPT-2 Medium and GPT-2 XL. The predictions were accurate within 1 to 2%, even extrapolating across orders of magnitude. Now let's apply this to modern models. GPT 3.5 has roughly 175 billion parameters, giving it a capacity of about 630 gigabits. It was trained on approximately 300 billion tokens, which represents roughly 4,800 gigabits of data. The dataset to capacity ratio is about 7.6 to 1. According to the scaling law, at this ratio, membership inference should be essentially random, completely ineffective. And this matches recent empirical findings. Researchers attempting membership inference on production models have found it fails on average samples. The models are trained on so much data relative to their capacity that individual data points become unrecoverable. For modern large-scale models, the average conversation or document is not vulnerable to membership inference. The sheer scale of training has made your individual data statistically undetectable. The exception, as we saw earlier, is rare or unusual content, which still gets memorized. But common, everyday text appears to be safe, not because of privacy protections, but because of fundamental information theoretic limits. So let's return to the questions we asked at the start. In the span of this video, what have we learned? First, how much can these models actually store? The answer is precise and quantifiable, about 3.6 bits per parameter. For a model like GPT-3, that translates to roughly 79 gigabytes of pure memorization capacity. That sounds like a lot, but it's only 4% of the training data. The remaining 96% must be compressed into patterns and generalizations. Second, can we distinguish memorization from learning? Yes. The key insight is comparison. By measuring how much better a trained model compresses data compared to a reference model, we can separate sample-specific memorization from pattern-level generalization. And models do both simultaneously. As datasets grow beyond capacity, models shift strategy, trading individual memorization for reusable patterns. Third, are modern models vulnerable to privacy attacks? For most data, no. Models like GPT 3.5 are trained on datasets so large relative to their capacity that individual data points become statistically unrecoverable. Membership inference approaches random guessing. Your average conversation or document is safe, not because of explicit privacy protections, but because of fundamental information theoretic limits. But there's a critical caveat. Rare and unusual content still gets memorized. If your data contains highly uncommon phrases, underrepresented languages, or unique combinations of information, it's more vulnerable. The memorization capacity isn't distributed evenly. It concentrates on the outliers. The broader lesson is this. These models aren't black boxes. We can measure what they remember, understand how they learn, and predict their vulnerabilities. The limits aren't just practical, they're mathematical, and that gives us a foundation for building safer, more trustworthy systems. Thank you for watching. We hope you enjoyed this video on large language model memorization. If you found this interesting, please subscribe to our channel for more content on related topics. Your support helps us create more in-depth educational material. You can also support us on Patreon, where you can suggest future video topics, ask questions directly, and receive early access to new content.